Good afternoon, this is Andy Schweitzer talking today about some actual calculations of velocity, acceleration, possibly even some displacement. Um, so some of this stuff might be very obvious, some maybe not so much. Our core idea of velocity is um, this formula right here, which is going to be your distance change. Again, this can be expressed as the difference in your displacement versus your difference in your time. Um, Anyways, the change in distance divided by change in time gives you velocity. If I'm graphing this, you would see that in XY coordinates, draw like this, that if I have, let's make this your distance or your position, and if I have a consistent change in distance per consistent time, I would have a either increasing a positive velocity, or I would have a negative velocity. Now keep in mind that this is just zero reference point of position. So the fact that it crosses that line just means we've passed a certain reference point position-wise. Otherwise, we have positive velocity and we have negative velocity here. The velocity is the slope at this point, and this is the slope of this guy. If we were to graph it this way, where we're having velocity versus time, that's a different situation. We have zero here, now that marks out zero velocity. So if I were to travel and stop, turn around, go away, I'd stop. Anytime you stop, you have to cross the zero threshold. So if a ball is moving, you could say you have a positive velocity here. Well, in this case, velocity divided by time, this would be considered this slope, this point is your acceleration. So this would be increasing acceleration. I could have a point where I cross this line, and that point we change actual direction. This is the positive velocity side. This is the negative velocity. So this is an actual shift of direction. In a stark change from a positive to a negative. You can have changes also. Anytime you're accelerating, to be changing as well. All right, so those are your calculations. Now, again, given any of these data points, I would want to be able to solve the other ones. This is another important calculation that's maybe a little more intuitive, but if I'm traveling, my velocity, let's say, is at, or speed, could be at 50 miles per 1 hour, and I multiply this times 1 hour, then the hours cancel and I get 50 miles. So at this point, velocity times time is the distance traveling. Keep in mind your units when you're dealing with things. The hours there, they cancel out, and I think that's about it for that. Let's look at another type of calculation here. Looking at maybe average velocity. Now, if I were to take a instantaneous velocity versus an average velocity, so let's say I take a position time graph, so go position and then time, and if I were to, let's say, travel like this here, I have no velocity here because I have no position change. And also I start to increase, okay, then I stop, then I increase, then I stop, I go to back, okay, so at this point I could say, okay, what is my net difference from here to here, my position, okay, and that would be simply this point right here. Okay, if I want to do an average velocity, that is the total change in distance versus some amount of time. Let's say point A to point B, all right? We usually do distance final minus distance initial over time final minus time initial. So that in this case would be B minus A, your total net difference. Anyways, this would be an average. Now again, technically, if I were to go from point A, travel to point B, and then travel back to point A, technically I have traveled zero distance. That's about zero. I haven't gone anywhere. I've come back to where I am. I could have a undefined, average velocity. Now I could say, okay, what's the total distance if I travel x and x? I could say, okay, well, I have 2x divided by my time. Okay, that would be what's my average speed. Okay, this is average speed, which doesn't really take into account the distance, the direction. I could take a different time frame here. I could say, well, what's my average between x and let's say y right here, these two different points here. In that case, because I have a straight line, I have a consistent velocity across that entire distance. And therefore I would have the same velocity all over. And to get an actual exact velocity at an exact point sometimes is easier than said than done. Again, these flat spots are easy, but if I had a position time graph where something is arcing, well then to get an actual velocity at a specific point might require higher mathematical calculus of some sort. Not that difficult, just something you have to use a little bit different mathematical tools to get. So average is over a large amount of time. Now, to actually calculate this, another way of doing this, and I'm going to give myself a little more room. Give a little more room here if I get that bar out of the way. This little calculation here is what we just talked about. Essentially, if you take a velocity final plus a velocity initial, you get your two velocities, your velocity total, and then divide that by two values, 1 and 2. That gives you your average. Okay, so in this case, again, you have velocity final plus velocity initial divided by 2 is your average velocity equals your change in your distance divided by your change in time. So at that point, we now have this equation, your change in distance. This is a very important velocity as well, important formula as well. All we did was we multiplied this time cost to get this one time over here, and this is a very important calculation. So average velocity is probably the biggest thing here, and then of course we have a slight manipulation to get our change in distance. Our next formula here is acceleration. Of course, if we have two graphs here, we have a position graph, position versus time, then the slope, in this case, if we like that, the slope is equal to position divided by time. That is going to be velocity. Okay. Now, how this changes, how the velocity changes, you get a velocity here, you can get a velocity here. How these velocities change is what dictates the difference in the velocity acceleration. So this formula is pretty standard, similar to your distance formula, but we're doing velocity. Change in velocity over change in time gives you acceleration. Okay. Now, if I were to do a graph that looks like this, we have velocity on the x-axis, and we have time on the, velocity on the y-axis, time on the x-axis. Then, for example, something falls, it might be increasing in speed at a certain direction, or like this, or it could be something like this right here. In this case, we'd have a positive acceleration, and we have a negative acceleration. Again, in this case, the slope is equal to acceleration. Okay. Velocity is very often referred to as the derivative, which means it's the the slope of a position time graph, and the acceleration is offered as the second derivative. Now, if you manipulate this equation a little bit, multiply the t over, isolate vf, and you get the velocity final, which is a pretty common situation here where we could take the initial velocity, which is lots of times something could be stopping, sitting it still. Let's say you push a rock off of a hill, okay, it starts accelerating. Then you could figure out how fast something is going after a certain amount of time exposed to a certain amount of acceleration. So this is pretty common here as well. We'll probably do some examples of these in a next video. Thank you.